Hi, all. This is Vasu Sham, and we're Theoretically Podcasting. I'm joined today by my friend, former collaborator, Evan Coleman. How are you doing, Evan?
I'm doing great tonight. Yeah. How are things over in the West Coast?
No, there, the way you left them. So Evan did his PhD at Stanford, and it was around the time when he was wrapping up that I got to meet him and work with him, which was great. But Evan's current position is in a quite different field. In particular, it's in climate science, broadly defined. But could you maybe elaborate a little bit on both your role and the way you got there?
Yeah, for sure. I think climate science is maybe a little bit generous toward my scientific ability. I think uh, I my skills didn't directly translate to things like atmospheric dynamics, which is what I associate with climate science. But what I'm in and what we generally call our field is climate change mitigation and sustainability science.
Okay.
So basically, if you accept that climate change is going to happen, that some degree of climate change is baked in to our future, how do you take steps now uh, in at the level of policy, but also technologically, what sort of innovations are required to bring us below 1.5 degrees centigrade, 2 degrees centigrade by 2100. So those are the kinds of questions that we grapple with as part of this consortium. I'm formally am a postdoc at the MIT Climate and Sustainability Consortium. It's a new program. It's about 3 years old, and we work with directly with certain member companies who collaborate with us on research that's relevant to them achieving their climate and sustainability goals. They make commitments to reach net zero and they're serious about them. So, how can we help them solve their technological challenges to get there? So that's I can talk a little bit more about why that's the case, but yeah, how does that?
No, that sounds perfectly adequate as an answer. And indeed, it's a very interesting direction you went in, and I suppose the need for it is almost self-explanatory, as in the need for someone to do it. But what I guess one basic question is just before we get into any of the sciences, what made you aware of this program at MIT? I mean, what else were you looking at? Because one of the things that's, not entirely evident, if you are thinking about, you know, changing fields, at least coming from high energy physics, is what the opportunities are that lie in anything to do with climate change mitigation or anything of the sort. Maybe you go work for Tesla is kind of an idea that comes to mind, but yeah, so it would be great to know for the benefit of other people who might be thinking about it.
Yeah, for sure. So it definitely was not an easy path. People are very welcoming in this community. Like I would say, there are a lot of people who switch fields, and the diversity of fields within climate and sustainability work is incredible. I basically, in my close to my final year of grad school, I sort of I had been taking classes on climate change work on sort of I figured it would be a part of my future. And so I had decided to educate myself by taking classes at Stanford. I think, you know, one class every quarter was basically enough for me to see, even though it wasn't a lot of time committed, um, reading the papers that I was exposed to and learning about the active scientific literature through these sort of grad classes, seminars, um, basically convinced me that not only is climate change an incredible challenge for our survival, but it's also an incredible scientific opportunity to identify relevant problems that are challenging in terms of technological development, um, that require specific or very broad physics expertise. So um, I felt the space was missing physicists, and decided to basically, excuse me, change change careers to explore these problems. I think that's the best way of putting it. There was no point where I was simply committed to changing. I just gradually felt that the research was speaking for itself, that climate change was a problem, and that a lot of capable, smart people need to start working on it to solve it. Um,
Okay, so that's a perfect segue into what the theme of our discussion today will be, which is some physical problems in climate science, which could use a little bit of insight from the broad physics community. And what I was struck by when we would just talk about these things over lunch or whatever, back when you were still doing your PhD at Stanford, was the scope and scale of the ideas and the technology. It really is an effort to try and reshape the world, in an almost literal sense. And this is a level of engineering ambition that I feel like our generation has not really seen, at least not directly. There was the space race, there was the Industrial Revolution, whatever, centuries ago, and all those times were very exciting. And we were born into a world where most of the innovation was happening in the realm of silicon chips and computers, and all were very happy about all of that. But very few things akin to the kinds of projects you were describing, involving either the manipulation or probing of the entire atmosphere, the atmosphere in some very large area, or problems to do with the structure of soils and all sorts of very interesting things. And I thought that perhaps it would be good to just give our listeners a bit of a taste of what these problems look like, and just to make them familiar enough to be things that they might want to think about.
Yeah, and maybe just to tack on to that some perspective, maybe just some scale information so that people sort of understand why this is such a difficult set of problems. We as humans, we can only survive a few hours without normal body heat, a few days without water, and a few weeks without food. So we have a hierarchy of needs, and we've built a pretty sophisticated society around us to account for and try to satisfy those needs. But we haven't really spent a lot of time optimizing that society to achieve certain goals beyond survival. And I think if one could phrase this new era as a sort of scientific or innovative revolution, the Industrial Revolution took advantage of thermodynamically convenient, low-hanging fruit like combustion to achieve our goals, which were, again, survival, but also the scaling of industrial society. Now we sort of have to put the cat back in the bag. We have to partially or imperfectly reverse spontaneous processes through the application of renewable energy, and the deployment of renewable energy to achieve, basically reversal of the damage that has been done. And so in so doing, there is a huge opportunity to bring the world to a better place than the one we started with. And so I just want to offer that framing that this is inherent to human beings, this problem. It's something that, comes from just trying to survive and take advantage of the tools at our disposal to survive. But by no means do I view day to day this problem as being unsolvable. And I think that we just have to frame it as a technological and innovative challenge. Yeah.
No, that's also another thing that I was also impressed by is this framing of it that made it um I should say a lot more inspiring than most of what you hear. And the sense that a lot of media would have us believe is that there's just a solution, which is some sort of Luddite paradise of doing away with most of what works in our modern society technologically, and just yeah, somehow or other, the shrinking our influence on the world, which doesn't really compute. I mean, perhaps there was a time where, despite it being counterproductive, it might have been a thing that would have had some net effect in some direction. But indeed, to do this, well, to sort of conquer our influence over the climate is a step towards conquering the climate, which is a step towards doing anything else that, in science fiction, we would be led to believe the species ought to do. Like, you want to terraform Mars, well, you better know how to terraform the Earth, right? So,
It is funny that people will talk about terraforming Mars before they talk about solving climate change. I do think that that's kind of ironic, but I don't think that we're in the realm of crazy. And so I will say that. Like, I think, um, you know, there are definitely places where we push up against the limits of what systems are capable of. I mean, I think like the direct air capture community for capturing and sequestering carbon dioxide directly from air, like they push very much against the limits of thermodynamics, and in terms of their energy consumption, right? But yeah, by no means is this an impossible problem. It just, yeah, it definitely pushes physical limits. And the question is sort of how can we deftly maneuver around limits or design systems to control physical systems in a way that aids us. So I think like the first challenge that I sort of sent to you, I don't know if you want to get right into problems,
let's
but
yeah, let's do that. So Evan was kind enough to share with me a set of a few problems phrased as some textbook exercises, which which um which we want to now put some bounties on. Let's put it that way. Okay,
yeah,
great. So is this the first you're referring to, or was it to do with
yeah,
the? Okay.
yeah, it's got number. I mean, I just usually I write these problems down for my own edification, and then occasionally I find some venue for them. But I don't, I don't think about these exact problems for a living. The problems that I work through day to day are somewhat different in nature. They still involve physics thinking, but they are really industrial scale solutions that have to meet the challenge of scaling to global markets. These are more sort of constrained physical challenges where occasionally I'll see that there are a large number of problems in this space that fall under the same class of
Hmm.
problem. And I will try to get at the essence of them from some sort of toy model or phrase it in that way. I really appreciate the people in high energy theory who can think in terms of toy models very effectively, and I think that this is like an attempt at emulating them. Um,
Perfect.
so the point here, and just to phrase it in like human language before getting into anything mathematical, is that you very frequently run up against problems where you have some constrained and contained physical system, and you're trying to control it for it to sit in some equilibrium, some unstable equilibrium,
Okay.
or it could be a chaotic system, a system that's very difficult to control. In other words, and your task is to use some sort of manipulation of say some potential field. So you generate some time dependent potential by manipulating this system, this matter, this whatever, And the question is really how good can you do for say a given energy input to modulate the time dependent potential? How good can you do at keeping that system in in an unstable equilibrium, like otherwise unstable equilibrium, um, given fixed energy budget? So the question really that I'm targeting here, and it sounds crazy that it should translate, but I'm really trying to get at something that's relevant to fusion energy. So Vasu, I sent you a paper on this. It's a recent work. It's a recent PRL where they basically use small fluctuations. They induce small fluctuations in a tokamak plasma, and
Right.
they're actually able to stabilize the plasma through this.
Very
And
nice. So I'll just share it just to make sure that we are on the same literal page. Is this the
yeah,
one?
yeah. So this is a very
Interesting. Sorry.
so just from July, yeah. And it's really cool work. They're basically able to keep to control this plasma in a way that could potentially give us a serious like edge in the energy transition by manipulating doing small manipulations of this plasma to keep it stable. And
Interesting.
yeah,
So just to pause for a bit, let's put it in a little bit more context. So there seems to be these edge localized modes, which seem to be a problem. Um,
not a problem. No.
oh, I see.
They're something that you can exploit. Um,
Okay.
you
So they're
exploit,
not a problem. I see.
not a problem. There's something that you use to control the plasma to achieve quasi-continuous exhaust.
Okay. So what is quasi-continuous exhaust in
it,
this
it,
context?
it almost isn't important.
Okay.
The point is really that suppose what is fusion about, right? Fusion is about trying to uh, get more energy out of this plasma than you put into it.
Indeed.
But you also have to, not only do you put energy into it to get it up to temperature, you also have to put energy into it to keep it stable. And that it ends up being a significant quantity of energy that you have to use to keep it stable. And moreover, the cost of having plasma shoot out of the ball in the center of the tokamak is enormous because it shotguns out and it can actually damage the metal casing. So those things are generally engineered to, I guess, like micron precision. I'm not 100% sure, but to some degree that it will degrade due to this. And you want to make sure that the plasma doesn't do this. You minimize the amount it does this, and they've shown that you can basically achieve some variant of this by exciting small localized edge modes. Um,
Interesting. So these modes are basically what stabilizes the plasma, is that right? So by
yeah. I mean,
great.
basically, it's what enables them to control the plasma. That's the way of
Interesting.
so a large number of small manipulations of the system requiring ultimately a small number of each requiring a small amount of energy to achieve accumulates to something that keeps the system stable. But
Okay.
the question is, what are the constraints on that? If I
Uh-huh.
want to
Uh-huh.
keep the system X amount stable by some measure, how much energy do I need to put into the system to guarantee at a minimum that it will be able to achieve that stability? So you could think of it
Interesting.
like there's a very simple way of thinking about it. This example is translated to like chaos language. Like if you had a double pendulum, could you
Okay.
actually statistically guarantee somehow that is there some phrasing, some observable that you could measure that's that gives you any control or any predictability over the system? It's a question you could very easily simulate it. The point is in these questions, you want to find through some sort of small manipulation, control a system or control outcomes in a chaotic or fluctuating system.
Interesting. So so we're in a chaotic phase or are we on the edge of chaos in this
In,
analogy?
well, in this particular problem, so maybe I can just sort of go through it. So you have a double pendulum. It has arms of equal length or whatever, just for starters. And you sort of imagine, say in MATLAB or something, you distribute the initial position of the second arm's endpoint uniformly on the circle of its extent. And then at times equals 0, you drop it, and and then a very short period after you drop it, it's gained some momentum. Um, you strike it just over a very short period of time from the right, and you impart some momentum onto it over that period. So if you achieve this, the question is there some sense in which there is a sort of probabilistic interpretation of x being less than 0
I see. I
after
see.
some
That's
time
what you
t?
want.
Yeah. So it's not, there's nothing significant about x being less than 0. Like, I don't care. Like, you could identify some other observable. But the point is there any sense in which I can control this system if I coarse grain time, or I do things very suddenly? Um,
Hmm.
so yeah, or in this case, if I coarse grain space, because I want to
Right.
see x less than 0.
Right.
So
Right.
so it's just, this problem appears over and over and over whenever you're trying to understand how to control advanced physics systems in a way that could potentially, by sort of sitting at the limit of what's possible, um, give us access to energy sources that we don't currently have, etc.
Indeed. Interesting. Interesting. I see. Well, no, that's actually very nice because as a statistical problem, what you're saying is that you want to know, you give me this dynamical system, um, what can one do to it to maximize some probability, right? So you define this observable statistically, right, over an ensemble of realizations of the dynamics, and say, how do I maximize this probability? And what's roughly the energy cost of doing that? And I think that that's very concrete. And for this particular problem, it might very well be that there's a solution somewhere. But okay, let's just
One
make a
can
note of
solve.
this. Hmm?
One can deal with this numerically. Like, I think actually this is a good problem to try numerically. I
Ah,
simply
okay.
don't, like, I write these things down, but I don't generally have the time to.
No, but this is great though. So the point is that if you can do statistics over um the dynamics of some chaotic system and get an understanding of some observables that are of the shape of what is the probability for the dynamics to be confined in some region, for instance, with the addition of some impulses or whatever. That's very much like, the kind of thing you deal with when you have a plasma or something of that nature. That's kind
Exactly.
of what you're saying. I see. And this is interesting because it is indeed a question of what in principle is doable, which is a little bit easier to answer than how to do it.
Yeah. And things like thermodynamics, I mean, we're very familiar with lower bounds from thermodynamics. So,
Mhm, mhm.
I think it may even be, and this is, a common thing. It's a limitation on my part, being one of the few people in the field that has a theory background. Um, it could be that the answers to these questions are already studied. I'm not somehow suggesting that these are necessarily new problems. I just think
Sure.
that it's going to be really important for us to be able to answer them. So if the answers are out there, great. But
Yeah. I'll leave them in the comments.
I mean, it could be that this is in what, the fourth volume of Landau. Like, it could be that I simply am missing something. But regardless,
No, no, sure.
I hope that
As I
works.
said, like let's just put them out there, right?
I mean,
And yeah.
right. Um, so yeah, that's at least that problem. But then, as I mentioned, these are global scale problems, and yeah, I think the next question that I sent to you is very much in that line of thinking. I mean, I'm not an atmospheric scientist. I've taken courses on tropical cyclones, but sort of the question that I have, and the question that's sort of common in the field, are sort of the numerologies, the sort of why we see the expected number of storms that we see each year. We only get something like 70 to 80, if I recall the number correctly.
I see.
Um, so being able to even estimate that order of magnitude from some physical model, that would be incredibly impactful. And so what this question basically does is it asks, if I have some sense in which there's like an average temperature of the Earth on a given day, say take steady state, like a lot of these atmospheric dynamics models, they model summer conditions, for example, so they don't even go through a whole year. So if you can find some sort of steady state configuration of the Earth over, I don't know, a month, a day, a month, a year, then assume it has some sort of average temperature, and there are some sort of fluctuations in that temperature due to the sun, literally heating the Earth, so that the daily maximum local temperature reaches some fixed value. You might have to profile this or model this somehow, but the point is that being able to understand how the expected number of storms changes based upon these parameters would be incredibly impactful, because it would tell us what we're supposed to expect. So as we reach 2 degrees centigrade average warming, do we expect a ton more tropical cyclones? That's bad, but we need to know that.
Right.
It's important information. Yeah.
Right. No, that's interesting. And well, here's a bit of homework that I did, which is to not actually solve the problem, but find someone much smarter than me who has looked into something that rhymes. I mean, I haven't done adequate homework to see if I can just solve the problem as you've stated it by just applying methods developed here. But Sasha Migdal has been also who's now at the NYU. He's been on a roll. So his beat has been to study fluid mechanics from an enlightened sort of field theory perspective, and it's quite interesting, really. This is a very rich subject, and for interested viewers, there's a great, really good talk by Sasha Polyakov, at the IHES from some number of years ago, where he explains how to use Clebsch variables and how to phrase the problem of turbulence as one of, you know, statistical field theory, to sort of see the emergence of some kind of conformal invariance and so on. So it's very, very interesting stuff. But this is a whole branch of research that sort of spun off from that. And Migdal, being one of the few people that understands these things in any amount of detail, has this very nice article from a year ago, and he has several follow-ups. But the claim here is that there's a steady analytical solution to the incompressible Navier-Stokes equations for arbitrary viscosity in an arbitrary number of dimensions, which represents a one lower dimensional vortex sheet. And this vortex sheet has some profile in the normal coordinate that is asymmetric. These vortices have set decay in either direction. In one direction, it seems to be Gaussian. The other direction, it seems to be power law. And this is an analytic solution. So very, very fascinating stuff. The basic trick seems to be to carefully look at this object, the space integral of the square of the vorticity, and cleverly reduce it using the Navier-Stokes equations and dropping some terms, and you get this to be a complete circulation integral. It reduces to a boundary integral. And what he manages to show is that you can basically solve this system, as in the minimization of this thing, by looking at some generalization of the so-called Berger's vortex sheet, which apparently had a Gaussian profile in the normal direction, just in general, but you have something more general and more asymmetric. So this is the Gaussian profile of the Berger's solution, but Migdal's found something asymmetric, which basically has a behavior like this. So this is the
Yeah,
velocity profile, and this is the vorticity profile. I mean, I don't know if this is what storms do, but I mean, I don't know. Like, it would be a thing to look at.
I mean, yeah,
Um,
I can sort of explain. This isn't too far away from, I guess, the spirit of what I was suggesting. And I mean, basically, I can explain that it is ultimately, I think, a two-dimensional fluid dynamics question. The atmosphere, to a decent approximation, is like a thin spherical shell. And convection is really important. So, I mean, I don't mean to like dismiss people who work on the full three-dimensional picture. That's definitely an important contribution. But if you somehow are able to dimensionally reduce the system, and instead just study it as two-dimensional fluid dynamics on the sphere, I do wonder if there's an opportunity to take advantage some of the sort of nice take advantage, for example, of the non-inertial frames point that due to Coriolis force, storms on one side of a hemisphere only tend to rotate in one direction. So because of that, I think what you could do is something like taking basically linear fluid vortices in the plane in two dimensions. Their complexified velocity potential looks like log z for z, the sort of complexification of the system.
right.
And if you take, d log z, you get something where if you contour integrate, you get, a residue.
Right.
And so the point is, if you take just one half of the Earth, say the below the equator, and you stereographically project onto the plane, and then you
Mm-hmm.
that contour integral of d, d phi, d log z over that area. Of course, there's curvature, so there are going to be some sort of strange effects of that. But I think locally, the linear fluid vortices will still look like log z minus z naught, right?
I see.
Uh,
So you're saying that you'd count some kind. This is going to be a winding number, basically, and you want to use this winding number to count the number of vortices.
and
Uh,
it won't be, yeah, I mean, if you do that, you're going to get something where time and energy scales enter into the problem. So you would need to know the average sort of length. You need to have some way of estimating the order of magnitude of the length of a storm, and you'd also need some order of magnitude scale to tell you what the amount of energy stored in
mhm.
this would look like. Um, but I think if you have that information and you also have some sort of reasonable steady state approximation, you could maybe even get it through numerical approximation. I think anything goes, honestly.
Right. Okay. Well, no, this is very concrete, and it's very interesting that it is a nice case, when you're in two dimensions, and yeah, it could very well be that there's some sort of coarse topological measure that you can fit these parameters into, right? Because that's ultimately what you're asking for here, is to get these numbers as function of some temperature for starters, and then you want to know more dependencies, which
Yeah, and how temperature translates into the properties of the fluid, I mean, there are many ways of potentially modeling these things. It doesn't necessarily, as long as you have some clear understanding of how the sun drives the solution, then it's all fair game. I'm not saying you have to accept my parameterization of the problem. It's more to say I phrased it this way because there is a very clear motivation for studying this problem, and it has to do with climate change. So, yeah, so that's
Interesting. No, that's great. That's great. It's exactly up the alley of quite a few people. But I do recommend that people check out Migdal's recent work. And if somebody understands it to any extent, I would love to have them on as a guest because it's a bit dense, I found. Or maybe I just haven't tried hard enough. But no, this is great. This is great. So we're going down the line, and here's the third problem,
oh
which
yeah.
I will just phrase as the following picture, and you can kind of explain what this picture is.
Yeah. So this is the right word is ternary. I always get the word wrong. It's the ternary phase diagram of soils. So this is, I think this picture is even from like the USDA website. It's a little bit unclear from the perspective of a physicist, like what does percent clay, silt, sand mean? It's basically a three-axis diagram where your soil can be made up of a certain percentage of components that have basically different particulate sizes. So sand has a characteristic size of something like 300 microns. Clay is somewhere in the realm of 30 microns, and silt is like 1 to 3 microns. So, or I'm sorry, it's the other way around. Sand is 300, silt is 30, clay is 1 to 3. I misspoke. The point is obviously these three numbers have to like add up to 100%, which is why you get this sort of strange set of axes. But the drainage properties are really the way that water percolates or penetrates through the soil is a function of these three variables, or really two independent variables. And it's a question, there's a lot of things in this field that are very much left unstated. And a lot of the time it's because farmers, for example, they just think it's obvious, like, oh, you just shovel some clay, you shovel some silt, you shovel some sand in this percentage, in this relative percentage, and you get soil that has really nice properties for growing food. But there's no like strict science to it. It's just like it's a thing that's done by feel. And so I saw this diagram for the first time, and I thought, it's really strange that it says nothing about the content, the nutrient content of those of sand, silt, and clay. All it says is something about the characteristic particulate size. And what this sort of prompts is through something as simple as like stacking spheres with a hierarchy between the size. So three species of spheres with some sort of hierarchy between their characteristic radii. Can you initialize them in some sort of random configuration where they have this percentage? Incidentally, I don't know if it's a percentage by mass or by volume. I go back and forth between the two. I can't figure it out. I suspect it's actually volume because of what I said about like farmers just shoveling, like, it's one shovel, two shovel. Like, I don't think it's by mass. I'm really not sure. But the point is, you mix that, you turn it up together. Can you simulate this numerically, or can you get some analytic understanding as to why the soil has the properties that it has? And is it true that the soil the only thing that matters is the basically the characteristic sizes of these particulates? If that's true, that gives us a lever. That gives us a lever to pull, because then that understanding enables us to control soils. Right. So if we could manufacture particulates that plants don't eat, and we could manufacture them very precisely at sizes and characteristic radii that sit, similarly to sand, silt, clay, or whatever, can we generate something like a hydroponic soil that doesn't need to be replenished, where it has the perfect properties that we'd like. It drains really well. You sit the nutrients into the soil you just put in solution phase all the nutrients that you would like to give to the plants. They have some fixed period of time to eat them. You drain it out, and you can maybe optimize farming techniques in hydroponic conditions this way. That is an idea or a thought or a modeling problem that has consequences that go far beyond farming on Earth.
Indeed.
Hydroponic we do in space currently. And it seems very sensible that if we do become an interplanetary society, that that you know that's some way of some critical knowledge for being able to farm in alien environments. So of course it's kind of like sci-fi crazy, but these problems, their solutions would be very broadly impactful. And
Indeed.
and
Indeed.
I love this problem because you never learn about this, right? Like I felt so cheated when I saw this diagram. I was like, soils have a phase diagram, and it looks so complicated. Like there's so many like beautiful phenomena that we just never really get exposed to in normal physics classes or anything. Because yeah, I mean we focus on the simplicity, on the beauty, but there are applications out there. Um, if you can understand something as complicated as this with a simple model. So yeah.
Indeed. Well, I mean, indeed, percolation is a famous critical phenomenon
Mhm, mhm.
that, you know, at least in low dimensions, has very nice relation to things like the Shambhala evolution and, all sorts of nice things. But, pushing this to a more three-dimensional setting, phrasing it as sphere packing, like all these things they're related enough to recent breakthroughs in various directions that one just has to wonder if pushing harder will just reveal avenues for a new sort of technological innovation. But I think that what we've done so far is perfect from the perspective of giving people the impression of what the large technological problems are and how their payoff is not just a matter of giving us a couple more decades to live on this planet, but really pushing us forward in what some would say is the human legacy of shaping the world, of maybe charting new worlds, but it's all just a matter of knowing not only how to exploit, as you said, simple thermodynamics, but to be able to push past, well, it's to be able to push past, just equilibrium situations. It's to know how to handle the interstices and being away from equilibrium, having control over chaotic systems, dealing with metastability and all these sorts of things. And I just think that it's great great to think in these terms because indeed with some of these examples we've already gone through, like let's just take that example that Migdal had. So I think that it'd be very interesting to go back here, but really to go to his recent uh, archive publications and see that there's an arc that starts with string theory and integrability, the C equals one string. So I could even show you. It's very neat that he has these sorts of statements. Well, it's not this paper, but there was basically a place where he was saying, well, look, actually, one of these fluid models, it maps exactly onto well, this is the same article, but anyway, he had this statement that it maps exactly onto the C equals one on like two-dimensional string theory. It's kind of crazy that you have these patterns repeating, in all these different places. But I think that like in general, my feeling is high energy physics has been a little bit confined in scope. I'm not saying that we need to take any turns. I just think that we need to sort of like expand the scope of application of the things we already know. And so it'll be really fun if some of them are relevant to technology,
Yeah,
honestly. Right?
I think that's a great way of framing it. I try to keep things in the positive. I mean, obviously it's sort of a survival mechanism in the field, but also like you I really like the idea. I think it's a beautiful idea that something so sophisticated and abstract could reach as far as, you know, a relevant problem in the here and now as we try to figure out how to survive in a changing, environment, a changing Earth system. So I view that as an opportunity, rather than just a challenge. It's a fun challenge, but it's
Yeah.
also, the premise of finding those applications at the very limit of, physics knowledge that we're capable of acquiring. That's I think that's beautiful, and I would love to have more people engage with these problems. I mean, I myself, like, I write these down because I don't have time to think about everything where a physicist is needed, and definitely, like, I'm actually told in my job that about 5% plus of my time has to be spent expanding the talent pool, because we need more scientists. We need more people getting drawn in to opportunities in this space, and they're growing. I mean, it seems like every other day I have friends on LinkedIn who are moving to something climate relevant. Um,
Awesome.
yeah, I mean,
Well,
the maybe I should just mention this, as sort of a last bit, but like, I think people don't necessarily understand that the IRA, the recent Inflation Reduction Act, passed by Biden, is going to basically guarantee, or at least according to estimates by Credit Suisse, something like $800 billion in climate tech funding, climate innovation funding, and energy transition funding. That is an economic shift already that's huge. That's a major fraction of the US budget deficit. And yet that's all going toward climate change mitigation. And I think, if you run the numbers and you ask how much is climate change going to cost, numbers are in the tens of trillions of dollars. So, okay, maybe our investment level isn't quite at the level it needs to be. But if you contextualize that in the context of other world events, World War II cost $4.1 trillion dollars. This is multiple World War II level expenditures. That's adjusted for inflation, by the way. So multiple World War II level expenditures on the time scale of multiple World War IIs, right? 30 years, 2050 is when we're targeting most of our solutions by. So yeah, I just see an enormous opportunity for intelligent people to get involved, trying to learn about and solve these very relevant problems that affect us in our day-to-day.
absolutely.
And if we end up with fusion out of it, I mean, that's amazing, right? Like, it's, of
Absolutely.
course, it's crazy, but it's also crazy, the world we live in. So I think there's something to be
No,
said
I think we don't have to worry about it being crazy, especially not. I mean, this podcast, we know our listeners.
about.
They're not worried about that. But I mean, the other point to make is sort of like, I don't know how to put it, but a corollary of what you just said is that if intelligent people don't get involved in all this, then well, it's only going to be the other people that do, and we're going to have to live with less than intelligent solutions, which aren't really solutions, to the problems we're currently facing. So I guess seen from that perspective,
Yeah, I'll be the carrot,
it's
you can be the stick. I'm not gonna. The point is,
that's a whole other podcast indeed.
there are a ton of smart people working on these problems all the time, but I don't think there's any harm in having more people, more hands on the problem, especially with different views. I work day to day with organic chemists, social scientists, anthropologists, finance experts, biologists, education experts, atmospheric scientists, metallurgists. Like, the number of different backgrounds of people that I work with is extraordinary, and I really do think this is an all hands on deck moment for humans, and yeah, I'm looking forward to seeing all of the amazing innovation that comes out of it. If some can come out of high energy theory, I think that's amazing.
Yeah, we'll have our time in the sun yet. Just you wait. But on that note, you've basically committed yourself to being a repeat guest. So
Oh no! All right.
as you have more and more problems that you think of and you write down, you can come here and we can go through them, and maybe at some point at least one will get picked up. Yeah. So, I mean, I do hope that there's at least one non-bot comment on this on this episode with either a statement to the effect of can solve that problem, or this has been known for a million years. So that would be ideal, I guess.
It's less work
Or
for
at least somebody who is inspired. Anyway, thank you so much for your time, Evan. And as always, pleasure discussing with you. Um, do you want to promote anything?
Oh, promote anything. No, I mean, all the amazing work that's going on in climate and climate change mitigation right now. I mean, I think MIT is a pretty central hub of all of this. Like, I've never seen a program quite like this. It's experimental in a kind of crazy way, but it's amazing, I think, what it's going to be achieving in just a short period of time. So I'm really happy here. Like, I think that this is the place that I didn't anticipate could exist for somebody with my background. But those opportunities are definitely out there. I am helping people find jobs. That is a part of my job. So
Interesting.
I'm very happy to talk to people. Maybe I can give my email or something, people can reach out. If you want to learn more about, how to get involved in this space, I'll do my best, to field you toward opportunities that are relevant to your interests. So
Right on. Awesome. Well, this was Theoretically Podcasting. If you got this far, please like, share, comment, and subscribe. And I will catch you all next week.